Let's go ahead and use the function we just coded. Let's call the result modified grade z. Modified grade z will be grade relu, which will take z and grad z. And its shape will be the same as grade z. So modified grad z dot shape 4/2. Let's make a quick recap of what we just went over. So we saw that the partial of the loss with respect to the wave vector of one neuron in the input layer wj was equal to the dot product between the partial of the loss with respect to zj and the partial of zj with respect to wj. We established that the partial of zj with respect to wj is equal to this modified version of the input matrix where every sample that results in a negative dot product with wj is essentially nullified. And we know that this is due to the ReLU function. We also saw that the modified version of the input matrix will systematically nullify some values in the partial of the loss with respect to zj. We took that fact into account and modified the partial of the loss with respect to zj to reflect the influence of the ReLU function. In doing so, we are now able to use the input matrix in the place of its modified version in the calculation of the partial of the loss with respect to wj. Let's actually go back to our code to make it happen. So we learned that the partial of the loss with respect to the wave matrix of the input layer W, let's call it grade W, is equal to the dot product between the input matrix X and the modified version of grade Z. Similarly to what we did for grade V, I changed the order of the elements here to obtain a matrix of the right shape. Let's actually go ahead and grab the shape of grad W. So grad W will be a 13/2 matrix. We have just obtained the partial of the loss with respect to the wave matrix of the input layer. And now that we have the partial of the loss with respect to all the weights in the network, we can move on to the next step of our batch gradient descent algorithm, which is to update the weights. We learned that to update the weights of an artificial neural network following the gradient descent algorithm, we need to subtract the step from the weights. The step being the learning rate times the gradient of the loss with respect to the weights. Let's create a variable to store the learning rate. And let's initialize it at say 0.000075. The learning rate is a hyperparameter that needs to be tuned in order to improve the performance of the network. If it's too small, the network will need a lot of iterations in order to converge, but if it's too large, the model might not converge at all. Let's go ahead and update the weights of our network. Let's start with wave vector V of the output layer. Learning rate times the partial of the loss with respect to wave vector V. Let's move on to the wave matrix of the input layer. Learning rate times the partial of the loss with respect to wave matrix W. There we have it. We have just coded our batch gradient descent. We only have one issue at the moment. If we are to run this code, our weights will only get updated once. In the second part of our series, we learned that the lowest value of our loss function is approached incrementally through relatively small steps. So what we need now is to repeat the calculations over multiple training iterations. A training iteration is also called an epoch. Let's go ahead and create a variable called number of epochs. And let's initialize it at 50. Let's also create an empty list to store the successive values of the loss function so that we can visually see how the loss function gets smaller and smaller as we move through each epoch. Finally, let's import matplotlib to plot the graph. So import matplotlib.pyplot as plt. In each epoch, we will have our forward pass, store the value of the loss function, and then proceed to our backward pass. So for epoch in range, number of epochs, we will have the forward pass and then store the value of the loss function and then proceed to the backward pass. And that's it. That's how an artificial neural network is trained. To visualize how we incrementally reduce the value of the loss function, let's plot it. And voila, that is it. We have just coded an artificial neural network from scratch without using any machine learning library. Let's actually go ahead and visualize how our network performs. As we can see, our batch gradient descent algorithm successfully reduces our loss function. Let's have a look at our latest training values in YPRED. As we can see, our predicted values are more realistic. Although our model is not 100% accurate as indicated by our loss function. We can further improve the performance of our model by tuning the hyperparameters such as the learning rate, the number of layers in our network, the number of neurons in the layers of our network, and the activation functions. This concludes our series on creating an artificial neural network from scratch. In this series, we have successfully coded a two-layered artificial neural network without using any machine learning library. We went over the key concepts of a neural network and we obtained some tangible results that the model is actually learning. Please let me know in the comment section what you thought about the series. Thank you for tuning in to work with me. I will see you in the next one.